Alrighty, so we have a lot of reading to begin with. Okay, with maximums and minimums and what they call extrema. Okay, which is the plural of extreme, right? So multiple extremes are called extrema. So maxes and mins. Okay, so the maximum is the highest y value on an interval, and the minimum is the smallest y value on that interval. Okay, so here we have some definitions of relative extrema, relative maximums, and relative minimums, also known as local maxes and local mins. Okay, so looking at this chart right here, our nice little initial points, tell me what the absolute maximum is on the closed interval from -2 to +4. Absolute maximum is 21. Okay? So our x and y values never change, or the x's are always there. So our x is not involved in an absolute maximum. It's the y value. Okay? Well, I guess, wait a second, so these ones are in fact asking for x values. At x equals what? At x equals 4 is where f has an absolute maximum. Okay, what about the absolute minimum at x equals what? -2, right? These are the x values where y is the smallest. And a relative maximum at x equals 0. Yes, 0 has a relative maximum right here, right at the top of our hump. And the bottom is at x equals 2. So these are all of your x values that we notice. So notice, what is x equals 4? What does that represent for our graph? And x equals -2. What do those two values represent for your graph? These are your endpoints, right? Now, +4 is the right side of our domain, right? That's our maximum domain. And -2 is the left side of the domain. Okay, so +4 and -2 represent your endpoints. If those are endpoints, then what are your 0 and your 2's representing? The what's? Well, call them right here. They're called critical points. But looking at the graph, what do you notice about their slopes? The slopes are 0, right? So here we have a maximum where we have a horizontal tangent that's 0, and you have a minimum where you have a horizontal tangent at 0. Okay, so this is going to be pretty important, is that we have critical values at the endpoints and wherever your derivative is 0. Right, because that's where we have a maximum or a minimum, because your graph changes from increasing to decreasing, or from positive derivatives to negative derivatives. That's where we're going to have a maximum or a minimum based upon what the change of sign is. Okay, so here we have your definition of a critical value. Either your derivative is 0 or not differentiable. So that means we come to a cusp, or probably not an asymptote, but not differentiable. So we have to check, where is it 0 or where is the derivative undefined? A vertical tangent line would be another point where where it's not differentiable. That means that C is a critical number. Okay, and then we have a critical point which has an x and a y value. So points have two parts, an x and a y, where a critical number is just the x value. Okay, so let's look at these 3 examples, and can we name the maximum and minimum points on each of these intervals? Okay, so our first example A, where do we find a minimum at? At x equals 0, right? X equals 0 is where our y value is the smallest. And we have a maximum at x equals 2, where the y value has the greatest, right? Where the y is the greatest value. Okay, letter B. Where does why does our function have a minimum? At what x value? At x equals 0 again, right? That's our lowest point. Then what about our maximum? Does this graph here, B, have a maximum? That's a question mark, right? No. No? Yes? At x equals 1.9? Or maybe at x equals 1.99? Maybe at x equals 1.9999999? Interesting. All right, what about our third one? Where does this one have a minimum? No? Huh? Does it have a maximum? At x equals 2. So why does number 1 have a min and a max, but letters B and C don't? Open circles, right? So open circles have to do with domain values. So what happens if we write the domain for A? What is the domain for A with 2 closed dots at both ends? Brackets, right? -1 to +2 is the domain for A. What about the domain for B? Bracket -1, but 2 gets a parenthesis, right? 2 has a parenthesis. So we don't have a maximum if we don't have closed brackets. Now what about the domain for C? That goes from -1 to 0, right? And then 0 has a hole. So we represent that with parentheses. And then it ends at +2. So it looks like we can say what conditions are necessary to guarantee a maximum in. We have to have our endpoints. Well, let's don't say that. There's a better word for it, and it begins with C. Our function has to be continuous on a closed domain, right? So here it's continuous up to 2, but then it's not continuous at 2 because there's an open circle. So, and then of course on C it's not continuous, it has a hole, a removable discontinuity. So the conditions are that it has to be continuous on a closed interval in order to have a maximum or minimum, which, if you flip your page over, is exactly what your extreme value theorem says. So we start off with the if. If f is closed on or continuous on a closed interval. So that condition must be met in order for you to have an absolute maximum or an absolute minimum in that closed interval. Okay? And it's going to happen at one of 3 different places. Number 1, it's going to happen at a critical number. So this is how we're going to use, this is called the candidates test. Okay, so sometimes you'll be told to use the candidates test to find the extrema. So whenever it says something about extrema, you're looking for the extreme value theorem. So it has to be continuous on the closed interval. And then we have, number 1, find the derivative and the critical numbers. Okay, the critical numbers are where the derivative equals 0 or undefined. Okay, so either where your derivative is 0 or where your derivative is undefined. So if we happen to have some sort of a rational function, right, we take the derivative of a rational, we have to use the quotient rule. So it's going to have some type of a denominator. So there might be places where your derivative is undefined. Those are part of your candidates for your extreme value theorem. Okay? And then you're going to evaluate those critical numbers, right? So you're going to plug them into f, plug these x values into your function, and see what the y values are. And then you also have to evaluate the endpoints. Okay, so your critical values are the zeros of your derivative and the endpoints. So let's apply this to here on A. So here we have a quadratic function, 3x squared minus 24x minus 1, and we're looking for the maximums and minimums on our closed interval from -1 to 5. Okay? So of course we want to figure out what f of -1 is, because that's an endpoint, and we're going to find f of 5 also. Those are also endpoints. Okay, so let's do that real quick. F at -1 equals. So here we have evaluated your endpoints, right? Because those are part of your critical values, the endpoints. And we got 26 at when x is -1, and we have -46 when x is 5. So now let's take our other one and let's find the derivative and its critical numbers. Okay, so f prime at x is 6x minus 24, right? So it's the power rule, 2 times 3, and then minus 24. And we want to know when will that equal 0. So we solve this for x, and we get x equals 4. So our other critical number, besides our endpoints, is x equals 4, right? Because that's where our first derivative is 0, and where our function will have a horizontal tangent line. So now we have to evaluate f at 4. So now let's look at our values. Where do we see the lowest value of y? So f of x has a minimum, maybe an absolute minimum. Yep, an absolute minimum. Let's write that instead of just minimum. Absolutes. And we can use shorthand. That's okay if you write ABS. Or you can write out absolutes. So AP will recognize ABS as standing for absolute. Absolute minimum at what x value? At x equals 4. Okay, the y has a minimum at x equals 4. So our answers are always x values. And f of x has an absolute max at what x value? At x equals -1. Okay, so we do the work to figure out what our y values are, but your answers are x values. F of x has a maximum when x equals 4, a max when x equals -1, and it has a minimum when x equals 4. Okay, so it's not asking you what the maximum and minimum values are. They want to know what are the x values where that occurs. Okay, let's first go ahead and calculate our 2 endpoint y values, right? We know we have to do that. Those are part of our critical values, so let's do this first. Now, let's take the derivative, which is 18x squared minus 24x cubed. And we also want to know when that is equal to 0. So I'm going to factor out a -6x squared from each of these terms, because now I can set each of my factors equal to 0, and I can solve and see when each of these have a horizontal tangent line. So I have a horizontal tangent line at 0, and I have a horizontal tangent line at 3/4. So let's evaluate f at 0. Well, that's pretty easy. That's just 5. But now we have to evaluate at 3/4. So I'm going to plug that into my calculator. So these are my values. So looking at my y values, it appears that I have an absolute minimum at x equals 2, right? So f of x has an absolute min at x equals positive 2. And it looks like we have an absolute maximum at that 3/4 value. So f of x has an absolute max at x equals 3/4. So we check the endpoints, and then we take the derivative and figure out where they're either 0 or it's undefined. So we haven't had any undefined values just yet, but give it time. I'm sure there's going to be one soon-ish. Okay, we have 3x to the 2/3 power, which I am rewriting, of course, as the third root of x squared. So when I evaluate -1 and +8, these actually come out to be nice values. So at our left endpoint, we have a y value of 6, and at our right endpoint, we have a y value of -3. So now it's left to find our derivatives. So f prime is 2/3 times 3 is 2. So 2x to the -1/3 minus 2 is my derivative. Okay, 2x to the -1/3 minus 2. And I want to know, when is that equal to 0? Let's add 2 to both sides. So this is 2 over the cube root of x, right? With the x to the -1/3 power is the cube root, equals 2. So I think the only way we could have 2 divided by the cube root of something and get 2 is if x equaled 1. So x equals 1 is my critical value. So let's evaluate f at 1. Probably 3 minus 2 plus 1 is positive 2. Okay, so it looks like we have an absolute minimum when x equals 8, and we have an absolute maximum when x equals -1. Okay, let's move on. So our last example is a trig example. So let's evaluate our endpoints, 0 and 2 pi. So both of these have y values of 1, because the sine of 0 is 0. The sine of 2 pi is also 0. The cosine of 0 is 1. The cosine of 2 pi is 1. So our answers are just 1. So now we have to go to our derivative. So the sine of 2x, the sine squared of x is going to be a chain rule derivative. So first we take the derivative and we bring the 2 to the front. So 2 times the sine of x, right, to the first power, times, what's the derivative of sine? Cosine. So our sine squared derivative is 2 sine x cosine x, plus the derivative of cosine is negative sine x. And we want to know, when will that be equal to 0? Okay, so let's see. Let's simplify. Here we have 2 sine x cosine x minus sine x equals 0. Okay, so just like up above, we're going to factor. Because what do each of these two terms have in common? They both have sine in common. So I'm going to factor out that sine, because the only way that I want to solve this is by factoring and setting it equal to 0. So if I pull a sine out of that first thing, I have 2 cosine x left. And if I pull a sine out of sine, sine divided by sine is 1. So I have 2 cosine x minus 1 times sine x equals 0. Okay, so let's see how many answers I'm going to get. I will get one answer where sine equals 0. And I will get some answers where 2 cosine x minus 1 equals 0. Okay, so each of these problems, we have to solve them by factoring. So we had a couple of quadratic factors, right? We had some common factors up above in part B, and here we have some trig factors. So where are the angles where sine is 0? That happens at 0 radians and pi radians. Okay, the sine is 0 at 0 and pi. Well, we've already tried 0, right? We've already plugged that one in. We don't have to plug that one in again. So we have to check on pi. What's our y value at pi? Okay, and then over here, 2 cosine x equals 1. If we solve this for x, right, we add 1 to both sides. 2 cosine x equals 1. That means the cosine equals 1/2. So where are all of our angles where the cosine is 1/2? Well, that happens in the first quadrant at pi over 3, and that happens in the fourth quadrant at 5 pi over 3. Okay, so we have to do 3 more evaluations. We evaluate it at pi, we evaluate it at pi over 3, and we will evaluate it at 5 pi over 3. Okay, so we're going to go back into our original equation of sine squared plus cosine and see what we get. So using my wonderful unit circle, I see that I have an absolute minimum, right? -1 is my smallest value when x equals pi. And I have 2 absolute maxes, right? I have a 5/4 and another 5/4. So absolute, I guess a local max at pi over 3 and another local maximum at 5 pi over 3. So remember, the answers are x values where we have the largest or the smallest value for y. On the closed interval, as long as our function is continuous on that closed interval. Okay, have a great day. Goodbye.